Find the maximum sum of any three consecutive numbers in this array. Sounds simple. And it is, if you're willing to redo work you've already done. But the way you solve this problem is the difference between a trick you use once and a pattern you'll recognize in 10 different interview questions. This is sliding window. Instead of recalculating from scratch every time, you carry forward what you already know and only update the small piece that actually changed. Here's the instinct almost everyone has first. And it's not a bad instinct. It's just incomplete. Check every group of 3 numbers. Add them up. And keep track of the biggest sum you've seen. It's correct. It will get you the right answer. The question is whether it gets you there efficiently. Watch closely what happens when the window slides over by just one position. We already added the 1 and the 5 that are still inside the window. We're about to add them again. From scratch. Just to account for one number leaving and one number entering. Scale that up. For an array of size n, checked with a window of size k, you're doing roughly n times k additions total. If k is small, that's barely noticeable. But if the array is large, or the window itself is large, the vast majority of that arithmetic is just repeating work you'd already finished a moment earlier. Here's the realization the entire sliding window pattern is built on. You don't need to recompute the sum of the window every time, because you already computed almost all of it a moment ago. When the window slides forward by one position, exactly one number leaves it on the left, and exactly one number enters it on the right. Everything else in between hasn't changed at all. So instead of adding up 3 numbers from scratch, we do 2 tiny operations. Subtract the number that just left, and add the number that just entered. That's the entire update. What used to take k steps every time now takes a constant couple of steps every time. And across the whole array. That turns an O of n times k algorithm into a straightforward O of n algorithm. One pass. Constant work per step. Let's trace this properly, one step at a time, so the mechanic really sinks in. The window starts at index 0, covering 2, 1, and 5. That sums to 8. Since it's the only window we've seen, it's automatically our best so far. Slide the window right by 1. The 2 falls out on the left, and the 1 joins on the right. Update the sum. 7. Not an improvement. So we keep going. Slide again. Drop the 1. Bring in the 3. New sum. 9. That's a new best. One more slide. The 5 leaves, the 2 enters. Sum is now 6. Not an improvement, so we keep going. And that's the whole array covered in a single pass. Every window checked exactly once. No repeated work anywhere. The maximum sum of any 3 consecutive numbers is 9. Fixed windows are the friendly case. Because the window size never changes, you always know exactly how many elements you're looking at. Real interview problems are rarely that generous. Here's where it gets genuinely interesting. What if you don't know the window size in advance, and you're actually trying to find the smallest window that satisfies some condition? This is LeetCode 209. A very commonly asked problem. Find the smallest contiguous subarray whose sum is at least 7. The core idea still holds. Grow the window from the right. Shrink it from the left. But now both pointers are doing real work. Grow the window by adding numbers on the right until the sum finally reaches the target. The moment it does, don't just record the length and move on. Try to shrink the window from the left as much as possible. Because a smaller window that still satisfies the condition is always a better answer than a larger one. You only stop shrinking when removing one more number would drop you back below the target. Add 2 to the window. Running sum is now 2. Add 3 to the window. Running sum is now 5. Add 1 to the window. Running sum is now 6. Add 2 to the window. Running sum is now 8. That's enough to hit the target. Window length is 4. That's our new best. Let's see if we can shrink it further. Shrink from the left. Remove 2. Sum drops to 6. That's below target now. So we stop shrinking and go back to growing. Add 4 to the window. Running sum is now 10. Still enough at length 4. But that's not better than what we've already found. Keep shrinking anyway. It might get better still. Shrink from the left. Remove 3. Sum drops to 7. Still enough, so we can shrink again. That's enough to hit the target. Window length is 3. That's our new best. Let's see if we can shrink it further. Shrink from the left. Remove 1. Sum drops to 6. That's below target now. So we stop shrinking and go back to growing. Add 3 to the window. Running sum is now 9. Still enough at length 3. But that's not better than what we've already found. Keep shrinking anyway. It might get better still. Shrink from the left. Remove 2. Sum drops to 7. Still enough, so we can shrink again. That's enough to hit the target. Window length is 2. That's our new best. Let's see if we can shrink it further. Shrink from the left. Remove 4. Sum drops to 3. That's below target now. So we stop shrinking and go back to growing. We've now walked the entire array with both pointers. Growing when we needed more. Shrinking whenever we could. By the end, the smallest subarray we found has length 2. Notice we never once went back and rechecked a window we'd already ruled out. Every step moved the pointers strictly forward. Which is exactly why this is O of n. Not something worse. Here's how you'll recognize. In an actual interview, that sliding window is the tool for the job. Before you've even started coding, look for 3 signals together. 1. The problem talks about a contiguous subarray or substring. Not any arbitrary subset. 2. There's a size, sum, or count condition tied to that contiguous piece. 3. You're asked for a maximum, a minimum, or something matching an exact target. See those 3 together, and you're very likely looking at sliding window. Longest substring without repeating characters. Contiguous. Size condition. Maximum. Maximum sum subarray of a fixed size. Exactly the first example we traced. Minimum window substring. Contiguous. A matching condition. Minimum. Different wording. Different surface details. But underneath, the same 2-pointer. Grow and shrink engine we just built by hand. So here's the whole idea. Compressed back down. Brute force recomputes the window from scratch every single time. Which is correct but wasteful. Sliding window reuses what it already knows. Subtract what leaves. Add what enters. And for variable size problems? It shrinks the window greedily whenever the condition still holds. That single habit of shrink whenever you can is what trips people up the first time they see it. And it's exactly what we just walked through step by step. This pattern shows up constantly once you know to look for it. Which is exactly why we're spending real time on it instead of rushing through. Next up, we're covering 2 pointers. A close relative of sliding window. And just as reusable once it clicks. If this is the kind of explanation you actually want more of. Full reasoning. Not just the answer. Subscribing means you won't miss the next pattern breakdown. See you in the next one.